We are on the doubly linked list section. I think you already learned how to make the doubly linked list in Python. And at this section, I would like to explain about the positional list. What is positional list? The positional list, it is to provide the general abstraction of a sequence of elements with the ability to identify the location of an element. So the point here is we want to know the location. So this is defined as the positional list. ADT is the abstracted type. A position acts as a marker or token within the broader positional list. So marker or token. It is like a kind of index. A position P is unaffected by changes elsewhere in a list. The only way in which a position becomes invalid is if an explicit command is issued to delete it. A position instance is a simple object supporting only the following method. So we want to see the P. P is the position, and then we have the method element. We want to see what is the element in the position P. There are some operations. For example, we can see the L first. We want to know what is the first element. L dot last, we want to know what is the last element. L before P. Because I know the position P, I want to check what is the element before the position P. L after P, I want to know what is the element after the position P. And yeah, we have is empty for all the abstract data type. If it is empty, then true. If it is not empty, then false. Length, we want to know how many elements in the positional list. Iter, it means we want to make the iteration for every element. And in the positional list, we want to have some kind of update operation. For the update operation, we can add, and we can add in the first position, or we can add in the last position. If we have the add first or add last, it means, yeah, if we have like this one, then we can add in the first or we can add in the last. But there is another kind of operation. We have add before and add after. Add before means I would like to add an element E before the position P. Here, insert a new element E just before position P. And add after P comma E means I want to insert a new element E just after position P. So if I know that this is the position P, then if it is before, then I want to insert in this position. If it is after, then I want to insert in this position. If I want to replace an element, then I can say that this one is the position at the position P. I want to replace with element E. So maybe I would like to update the element with another element. If you want to remove some elements in the position P, then you can just say that the L delete P. So this is the example. The table shows a series of operations of an initially empty positional list. So L, let's suppose empty at the first time. And for this one, we are not using the index like in the list. If you are using list, you have like index 2, index 0, index 1, index 3, index 4, and so on. If it is the list, but in the positional list, we can identify the position with different kind of index. And in this case, I'm using variables like P and Q and R and S. So we can have P, Q, R, S to indicate the positional list. For each exposition, the list contents are displayed with subscript notation to denote its position. So subscript means, for example, 8P. So this is the subscript in the below part, a little bit lower. So let's see the example. L at last 8. So I have the L, which is empty. Now I have the element 8 in the position P. So as I mentioned to you, I'm going to use P, Q, R, S. So I'm going to use the P at first index. I want to check what is the first. So the first will give you P. And then if I want to add after the position P, and I want to add a number 5, then I will have a written value Q, because the next variable is Q, and 5 will be added after the P. So the Q will be added after the P, and the value is 5. And next, I would like to add before Q. Oh, sorry, this one is not add before Q. This one is to check what is the before Q. Before Q is P. And I want to add before Q, comma 3. So before Q, it means I would like to make a new variable, which is R. And then R will be added before the position Q. We have 8P and 5Q. So before Q means I want to add before Q here. And the element that I want to add it is 3. So we have 8P, comma 3R, and then 5Q. If I want to check what is the element in the index R, then it will return 3. Okay, so R is 3. If I want to check what is after P here we got R. So we will see R. And what is before P? Because P is in the first, then there is no value, or there is nothing that we can return. At first, if you want to add something in the first position, so I will use the remaining variables, which is S, and then I put it into the first part of the positional list. So I would like to add 9 with the variable S. Let's suppose I want to delete. And what I'm going to delete is the last element. So the last element is 5q. So it will return 5 and the 5q will be deleted. If I want to replace p, 7, we know that p is 8. So when we are modifying the element from 8 to 7, we can get the return value is 8, and then the element in the position p is changed to 7. We can make our positional list in Python something like this one. We can have the class position, and then this is the constructor. In the constructor, we have container and node, and then we indicate what are the elements, and then we want to check whether the element equals to some of the position, and then not equal. NE means not equal, EQ means equal. We can have to validate whether the node is valid or not. This is the utility method, like make the position. And yeah, those are the methods that we already learned from the positional list section. First, we want to see what is the first. Last, we want to see what is the last. Before, after. Okay. And then we have the iteration. And we still have the insert between, like what we learned on the doubly linked list. And then we can add the first, we can add the last, we can add before, add after, delete, replace. So we can make some functions to define those particular methods or particular operation in the positional list. Yeah, as a summary, we can say that the linked list can be in the term of singly linked list, which has one connector to the next of the element, one connector to the next element. For the doubly linked list, we have the connector to the next element, and the next element have connector to the previous element. And yeah, there are many other kind of linked lists actually, but I cannot explain all. Let's say this is another kind of linked list. We call it as the circular linked list. In the circular linked list, it is similar with the queue. When we have the queue, yeah, if we are connecting this one with the other element, and let's suppose we have we don't have the trailer and we don't have enough capacity for storing all the elements, then this n or the last element will connect to the head node. So we call this is circular linked list, and yeah, there are still many other, but I guess you are enough with the singly linked list and doubly linked list. Okay, then I will continue with the tree. I'm not sure if I can finish all, so let's see. Until now, we learned the basic data structure like stack, queue, singly linked list, doubly linked list, array. And we also learn how to make the algorithm like the recursion. There is another kind of data structure, we call it tree. We will learn the basic definition of tree and how we can learn the traversal of tree and some kind of other tree. I'm not sure if I can finish all, but let's see if maybe I can just give you the basic and the pre-order and post-order. The tree ADT, we call it tree because we have something at the root. We call this is the root. And we can something on the leaf. So the idea is like, how if you want to make manifest. So some people say that, okay, I can make the stock fraud, or I can make the Ponzi scheme, okay, or I can do bank robbery. So this might be like the alternative. That's why we can make a kind of tree. In the computer science, a tree is an abstract model of a hierarchical structure. So it is a hierarchy. A tree consists of nodes. So we call this is one node. This is one node with a parent-child relation. There are some applications like the organization charts, or we can have file systems, or we can also do this one with the programming environments. So this is three examples. Let's say I have a company, computers, and then the company has a sales department, and there's a manufacturing company, and there's another department, R&D, research and development, for example. So the sales has been decided in US and other countries like the international countries. And the manufacturing can be divided into some other departments like laptops and desktops. The international can be divided into some other related countries like Europe, Asia, and Canada, and so on. Then we can see, yes, this is kind of structure. In the tree, there is a terminology. We call it root. Root means node without parent. So A is a node and there is no parent. There is no node above A. We call internal node. It is node with at least one child. So we have A, B, and C, and F. A, B, C, and F. We call this is internal node because the node has child. The meaning child is, we have the next node after this node. We have external node, or as known as leaf. It means node without children. So we have E, I, J, K, G, H, T. E, I, J, K, G, H, T. Those are the external node, or in many literatures they call it leaf. Ancestors of a node. There are ancestors. Ancestors means the upper part. The parent, grandparent, grandparent. So, for example, what is the parent of I? The parent of I is F. Okay. What is the grandparent of I? The grandparent of I is What is the grandparent of I? The grandparent of I is A. Okay. So in this case, we have like 3 depth of the structure. So we have 1, 2, 3. So the parent is directly the above, and then the grandparent means 2 above of that node, and then grandparent is 3 above that node. We have depth of node, so it means the number of ancestors. So if it is grandparent, yeah, the depth of the node is 2. If it is grandparents from I, then the number of ancestors are 3. The head of the tree, it is the maximum depth of any node. The maximum depth means, yeah, I have 1, 2, 3. So the maximum depth is 3. And descendant of a node, we have child, we have grandchild, we have grandchild. If we have the parent, we go to the above, and above. If we are checking the child, then we go to the below, and below. Okay. We can have subtree. Subtree means tree consisting of a node and its descendants. So we have the tree, and here we have another tree. So this tree, we call it a subtree because the tree consists of a node and its descendants. A node and its descendants. In the tree ADT, we can use positions to abstract nodes, and there are some generic methods. We want to know the length. We want to check whether the tree is empty or not, and then we want to do the iteration of the position, and we can do iteration for each of the elements. The accessor method, I want to check what is the root, what is the parent of the position P. I can check for every children of the position P and the number of children at the position P. We can have query methods. I want to check whether the position P is a leaf or not, or a position P is a root or not. And if I want to update the method, I can replace, and the replacement takes place on the position P with object O. Additional update methods may be defined by the data structure implementing the tree ADT. So this is the tree class in Python. We have the position. Position is the class. I think we already learned from the previous positional list. And we have the element equal, not equal. Now we define the tree. We have root, parent, number of children, and the length. And we want to check whether it is root or not, whether the respective position is leaf or not, or whether the tree is empty or not. when we are having a tree, we need to traverse. What does it mean by traverse? Traversals means travel. When you travel means you want to walk from one node to another node to next node and to the end of the node. So a traversal, yeah, maybe we can make it as a travel. A traversal visits the node of a tree in a systematic manner. So we need to arrange which node that we need to visit at the first time. We call it pre-order. Pre-order traversal, a node is visited before its descendant. So let's say I have this application, a print a structured document. So I want to first the root, and then next is in the left, and then I will go to the left. After I finish this one, I will go to the next node of this respective parent, and then if I finish with the left, I will go to the next node from the same parent, and then I will have right to the right, left to the right, and then after we finish, we will go back to the parent and then check on the right. So we call this is the pre-order V. V is the vertex or the nodes, and let's visit V. If V is visited, then for each child W of V, we will do recursion. There is another kind of traversal, we call it post-order traversal. In the post-order traversal, a node is visited after its descendant. Node is visited after its descendant. So the application is to compute the space used by files in directory or its subdirectory. So if you want to know how many space that you already consumed in your hard drive, then you will see from the bottom. So the first document and the second document, you will calculate how big is the size, and then you will go to the parent. After you have this one, you will go to the next document in another folder. You will go to the other documents, and then you will accumulate it into one folder. And then you will check another document, and then you will combine all those into one folder. So you can see how many space that you consume in this directory. And we can have this kind of algorithm. We call it post order. So for each child W of V, we will do post order, and we will check if we visit the node or not. Binary trees. We call binary trees because the tree consists of two. The binary tree is a tree with the following properties. Each internal node has at most two children. So internal node has at most two. Exactly two for proper binary trees. So we have proper binary trees. This one is proper binary trees because two, exactly two. at most 2 children means if I have like this one, yeah, it is also a kind of binary tree because we have only one option. The children of a node are an order pair. Order pair means B and C, D and E, F and G, H and I. We call the children of internal node is left child and right child. So this is left, this is right. This is left, this is right. This is left, and this is right. Alternative recursive definition is a binary tree is either a tree consisting a single node, say a tree with a single node, or a tree whose root has an ordered pair of children, each of which is a binary tree. So we have like this. Yeah, this is also a alternative of the recursive definition. We can have some application like in the arithmetic expression or decision process or searching. So we learned already about the binary search tree. Okay, I guess I will stop here because there are some other things that we still need to learn. So the